Hello everyone, my name is Mohammad Reza Farhadi. I'm here with you today to talk and explain about a paper called Mobile Bot Rotation using Sound Source Localization and the Sensor Speech Recognition. So why is that important to us? Why we want to build robots that we can control them by just voice and talk? So in recent years, indoor mobile robots such as service robots, assistive robots have become more common. For those robots, interaction with human must be natural and intuitive. Otherwise, users find them difficult or frustrating to use. Speech is one of the most natural interaction ways between humans, of course. So since it does not require physical contact or special devices, it is why that communicating with robots by words and sound is so important. Vision-based systems have inherent limitations. They depend on lighting conditions, have a limited field of view, and cannot detect sound emitting sources. Audio perception offers several advantages. Like we said, unlike cameras, microphones does not require a direct line of sight. It means that a robot can detect a human even if they are behind it or outside of camera or outside of view. So audio sensing is also robust to lighting change and visual occlusions. From a human-robot interaction perspective, this is important because humans naturally expect robots to respond when they speak. So regardless of where they stand, these are the reasons that is actually really important to us to communicate with robots by words. So I want to talk about more core audio tasks that what we're gonna learn in this paper. So let's guess we have just two important core audio tasks here. One of them is ASR and the other is SSL. Actually, the ASR, which is automatic speech recognition, focuses on understanding what the user says by converting speech signals into text. So the second one, SSL, which is sound source localization, focuses on estimating where the sound is coming from. So usually this is expressed as a direction or angle relative to the robot. Individually, each task is useful, but by combining or mixing these two ways, robot will understand the comment and especially orient itself toward the speaker, which is crucial for us. So let's talk about more research gap. What are our research gap in this paper? Also, ASR and SSL have been widely studied. Many exciting approaches are evaluated only in simulation or laboratory condition. So other require powerful GPUs or high-end hardware, making them impractical for using embedded robotic systems. Additionally, much of recent work focuses on audio-visual fusion, which increases system complexity and cost. There is relative I'm sorry for that. There is relative limited work demonstrating a lightweight audio-only system that operates reliably on a real mobile robot in indoor environments. This paper addresses this gap by focusing on practical deployment rather than algorithmic complexity. So let's move on the other side. Let's talk about system overview and robotic model, dynamic model. So the robot is equipped with a 4-channel secure microphone array, which allows it to estimate the direction of incoming sound. Audio signals are processed in two parallel pipelines, one of localization and one of speech recognition. And the entire system is implemented with ROS, which amplifies communication between perception and control models. Let's move on to in the next slide. So picture below shows how wave-to-wake learn robust speech representation from raw audio self supervised learning. I just want to introduce what are human speech. Human speech is the input of the model, of course. No handcrafted features such as MFC or spectrum are used. The next one is convolutional neural networks, which the CNN extracts low-level acoustic features and downsamples the signals. So the output of the signal is actually Z, which is a latent speech representation. This latent representation captures local phonetic and acoustic pattern in the speech signal. So after generating the latent representation Z, the model splits into two parallel paths. The one is context representation C, and the other one is Q, actually called quantization representation here. And what are these? Actually, the first one, the C, is stage captures is the stage that captures the contextual and structure of speech, which is crucial for recognition, words, and comments. So the other one is the same latent representation Z that are passed to quantization model. Actually, this unit acts as a target label for self-supervised learning, similar to tokens in language models. And the last one is this is a model trained that is trained using contrastive loss. The objective is to make the context representation C close to current quantize target Q while pushing it away from incorrect ones. So let's move on the other slide. What are the algorithm that they use in this one? So actually, the system is divided to two algorithms. The algorithm one is a perception and decision making. Where should the robot? The question that answers it, where should the robot turn, and how the algorithm two is how does the robot physically turn. So actually, in algorithm one, we continuously monitors we monitor the microphone array, wait until speech activity is detected, ensures the system is ready, Rust running microphone available and everything, and understand. The second step is to understand direction. Actually, we're gonna understand the direction. It uses sound source localization, etc. And the third one is understanding content, which is ASR actually. And the four level is decision making, compress SSL and ASR inputs, select the most reliable angle, and pushes one final rotation angle to Rust. So the second algorithm two, is a motion execution algorithm. So it does not process audio and does not make decision. It simply executes the command produced by algorithm one. So that means it's not that much complicated. So I just want to know I would just want to explain the levels. The first level is command reception, and the second one is motion preparation that sets all linear velocities to zero and ensures the robot perform pure rotation in place. And the third one is direction selection, so which in a way that you want to turn clockwise or counterclockwise. So the motion execution is applies a constant angular velocity and stops once the target angle is reached. The experiment and results. Actually, in this one experimental setup, all experiments are performed on real mobile robot, not simulation. The robot used in a Churchill Bot 3 Wiffle Pi, which is widely used research platform. A Raspberry Pi 4 is used as the onboard computer, and a 4-channel circular microphone array is mounted on the robot and aligned with its front direction. The experiments are conducted in an indoor environment, which naturally includes the background noises. This makes it more realistic. So in the next slide, we have ASR performance evaluation, which is distant ASR, I will call that. So this subsection evaluates how well the distant automatic speech recognition ASR system performs. The author used a Wave 2 spec that we also talked about that, which is pre-trained and then fine-tuned on their collected distance speech dataset. So performance is evaluated using two standard matrices, VR and TR, which I will talk about it later, what they are. And the evaluation is conducted with different distances like 1 meter, 3 meter, and 5 meter. And the results show that the ASR system remain functional even at larger distances. So let's move on to the other part, the real-time performance evaluation. In this part, analysis whether the proposed system can operate in real time or not. Two timing metrics are defined: response time and turnaround time. The response time is time required to capture audio, process SSL and ASR, and the turnaround time is total time including response time and the physical rotation of the robot. So the result shows that response time is very low and turnaround time is higher. The main source of delay is network latency because the ASR model run on a remote server, not on the robot itself. And the key point is that perception and the control pipeline is fast enough that the bottleneck is communication, not computation. So in the other slide, we have application study. So in this slide, we know that we compare two configurations, a single microphone and 4-channel microphone array with beamforming. The result criteria show that the microphone array significantly outperforms the single microphone, especially as the distance between the speaker and the robot increases. This improvement is due to better signal to noise ratio and more stable direction estimation. So let's get a conclusion of this section. Using a microphone array is critical for reliable distance speech recognition and localization. So in this section, on the figure left here, I just want to talk about results. This just shows how VR works by increasing the step. Actually, best VR is 40%. We have here 40.38, and VR increases as distance increases. System remain usable up to 5 meters. So actually, this one illustrates the ASR performance is in terms of VR at different distances, showing that the system remain functional even at 5 meters in your environment. So the next one, the next figure shows the convergence of training and validation losses, indicating that ASR model generalizes well to distance speech data. So first, both losses constantly decrease or poach, which indicates that the model is successfully learning from data. There are no sudden oscillations or diverges, meaning that the training process is stable. Sorry, so this the large gap between training and validation loss would indicate poor generalization, but this is not observed here. So in the next slide, we have two tables. The first table converge the different HR configuration and show that incorporating a language model significantly reduce both VR and CR. Like here, we can see that the CR and VR are both actually errors. Decreasing them are a benefit to our system. So we can see that they both decreased here and here by using a language model, and is the numbers are really important. So in the next, another table shows that the system responds quickly at the perception level, while the overall turnaround time is dominated by network latency due to remote ASR processing. So what it shows is that timing analysis of the system, response time and turnaround time. And the key results is that response time is on milliseconds, and the turnaround time is on a few seconds. That they are really different to other. Okay, and the conclusion part. So, in the conclusion, the author summarizes the main contributions of the paper. They propose an audio-driven approach that allows a mobile robot to orient itself toward a human speaker by integrating SSL and ASR. A key strength of this work is that it does not rely on vision sensors or an environment map, and instead the robot uses only audio information, which makes the system robust to lighting conditions and visual collisions. So the system is implemented and tested on a real mobile robot and in real time, operating in an indoor environment. Experimental results demonstrate that the robot can successfully rotate toward the speaker even when the speech is distant and affected by noise. And although distant ASR introduces recognition errors, the integration with SSL ensures that the robot can still perform intended orientational task reliably. So this shows that perfect speech transcription is not required for effective human-robot interaction. Overall, the paper demonstrates that a simple and well-integrated audio-based system can achieve real-time performance on resource-limited hardware, making it suitable for practical indoor human-robot interaction scenarios. And I want to add just a few words. You can say this I can say this work show that combining distance speech recognition with sound source localization, SR and SSL, actually provides a practical and robust solution for real-time audio-based human-robot interaction in environments without light and other mapping resources.